Hi everyone, Andy from Protogen here. A couple of weeks ago, I once again had the honor of guest lecturing a class at Penn State University. The assignment at the end of the class was to take a building on campus and create a level 1 feasibility study conceptual design or basis of design, which is really just project development and engineering speak for rough draft. If you've never had to design a power system before and have limited experience with construction documentation, that can be really challenging, if not overwhelming. So, based on some of the questions I received and understanding that there are probably a lot of people interested in the basics of PV system design, I decided to create a few videos about how I would navigate this situation myself. It'll be a chance for you to kind of watch over my shoulder as I work, and I'll do my best to explain my process, my thinking, and where I go to get information along the way. The premise of the assignment was that I provided the 3D model. For this exercise, we're going to assume that you have a rough general model of your building that already ready for you to work with. So here we have that model in SketchUp, and this is where we're going to start our exercise. One of the first things that we need to do once we have the model built is understand what our offsets and our clearances are. You've got fire issues, you've got mechanical clearances, and then you also have electrical working clearance issues. So the first thing I want to look at is the requirements for fire code. So one of the first things I'm going to want to do is start laying out where I'm allowed to and where I'm not allowed to put modules on this building. So I would create a layer and just call it offset, plural. And then I'll be using that to figure out where to draw some lines in order to exclude places that I'm going to be putting the module. After I have that layer created, I need to start figuring out where can I and can't I put modules. So the first thing I would do is consider the fire codes. Depending on your location, you may or may not have really well-defined or easily accessible fire codes, but it's pretty safe to default to the IFC, the International Fire Code, or even CAL FIRE, the California Fire Codes. So what I'm going to do is bring up here on the left side of the screen the 2018 International Fire Code. If you scroll through the whole document and you read the table of contents, you get to page 219 or 20, where they start talking about solar photovoltaic power systems. They start off with access pathways, setbacks, pathways to the ridge. That's largely dependent on designing for residential buildings. This building that we're working with here is not a residential building, so it's not an R grouping. It is exceptions. So the first thing that you run into is perimeter pathways. That's a great place to start. But one caveat, because I see some of these roof obstructions are closer than where we're going to get to, let's first figure out a quick way to start drawing these lines. So what I'm going to do is I'm going to open up my group. You'll understand later why we like to have grouped items. I'm going to copy these three roof surfaces, and I'm going to go edit, paste in place, and then I need to move those to the offsets layer. Once I have those three items selected, I'm going to hide my building, and I'm going to select my obstructions. I'm going to right click on the faces of the roof. I'm going to say intersect faces with selection. Once I have that done, I can hide the obstructions, and I should have the outlines and the perimeters of all those roof items intersected and now as geometry on these roof faces. So one thing I'm going to do is there's a little bit of an error here. That's just because of my poor modeling practices to begin with. So all of a sudden, delete these elements. And now we start looking at the equipment on the roof. So if I go back to turn off the offsets and turn on the satellite view. This is the roof that we're working with right here. You can see this is an air handler. These look like skylights, so those are probably venting locations for firefighters. A little preview. This looks like a roof hatch, so a roof access hatch, probably over a stairwell. This looks like a roof access hatch as well. So we want to know that equipment, skylights, air handler, roof hatch. So if we turn offsets back on, kind of see this, and this are the skylights. That's also a skylight. These are roof hatches, and the rest is mechanical equipment. So we'll turn the satellite view off. Now, let's look at what the fire code has to say about smoke ventilation. So for ease of conceptual design, we're going to assume 4 foot off of skylights because they would be ventilation hatches. So the quick way to do that is, now that I have this geometry, I type O for the offset tool, type in 4 feet. I had to set O as a shortcut, so you may want to do that. Then to be quick about it, you then can just double click to repeat your command. That deleted exterior surface, that's okay. Equipment is also probably 4 feet, and we'll cover that a little bit later. So let's just, for safety's sake, add 4 foot clearance around all the pieces of equipment. And a little bit, 4 feet, yeah. Feet, 4 feet, 4 feet. That's HVAC. This is a standpipe. Probably delete that. E for the eraser. The eraser tool is cool in SketchUp because it doesn't erase faces. So that's a trick to know. Offset 4 feet, 4 feet. So now we can see the areas that we need to stay out of as far as access around hatches, skylights, etc. Now we have this piece of HVAC equipment. If we get rid of that, there's not a general consensus. I mean, there's some rules of thumbs for air handlers and equipment, but the best thing you can do is identify the piece of equipment and then go see if you can find a cut sheet or call the manufacturer. So what I've done is just taken out an example of a rooftop air handler. This is a train unit, and you can just download the installation manual. It's 80 pages long, but what you really want to close in on is dimensions. The dimensions is where they're probably going to tell you what the working clearances are. So we have that, page 58. So we'll jump to it. This is just a lot of dimensions of the unit itself. Been through this before. Here we go. Down on page 64, they've got this drawing here, which shows the door swings. And then over on this side, they say 6 foot minimum service clearance. And this side is an 8 foot minimum service clearance. And then you've got notes 1 and 2. Minimum clearance of 2 foot is 2.5 feet roughly is required to open the hinge controlled panel doors. And on this side, 2 foot 10 inches is required to open the others. So we said 3 feet. That's probably safe. So just for, an exercise example, let's do an offset of 3 feet on, that unit. And on this face, let's also offset 3 feet. But the one thing to consider was there's some long access required, 6 feet and 8 foot over here. So what we can do is just grab this and slide it on out. Just did 3 feet. Let's do 5 extra feet. 5 feet. And then that, we looked at the satellite view. That was just the back end of the equipment. So probably don't need 5 feet of clearance over there. But we won't add any extra. And then we want to get these roof surfaces back, so you can just draw a line. And then if you wanted to really clean this up, you could just use the erase tool to start erasing your interior geometry. But most of this is going to be hidden under your other geometry anyway, so it doesn't really matter. But for the sake of time, unless you're working along, I'm not going to go through and delete all of this. Made a little there, carried away with the mouse. Middle mouse click and hold shift. That's a pan command. That's pretty convenient. Very useful to speed up your navigation. A couple more over here, just to be thorough. There we have it. Now, one thing we want to do now that we have this geometry here, we'll delete these surfaces. You can even delete these interiors, because at the end of the day, for this part of the exercise, we just want the line work. So what I'm going to do is highlight everything. Group. There we go. We want to make sure that that's on the offsets layer. So now when you bring the building back and the obstructions, you can see we have these areas that we shouldn't put solar panels. One other consideration is the electrical working clearances. So if you had inverters on the roof, if you knew where you were going to be putting those, you'd want to make sure you refreshed your memory from the electrical code. And I have some notes here. Section 110.26A1 is where you're going to get the working clearances for most electrical equipment on a building. We're assuming that that's low voltage, 0 to 1,000 volts approximately, and that'll all fall under that table. And this building's probably 208, 480, and most of that equipment requires 36-inch working clearances and have a width requirement outside of the panel, but you can just look that up. See code. So now that we have our clearances sorted out, we need to start considering putting modules on them. So the first thing that we're going to want to do is create a new layer, call it modules. Extra capital O, concerned about that. And we're going to need to draw a module. How do you draw a module? Well, you don't want to just draw a rectangle. You want to draw a dimensionally accurate rectangle. And the easiest way to draw a dimensionally accurate rectangle is to get a cut sheet. For the purposes of this exercise, we're going to use a 365 watt LG module. Bigger so that everybody can see it. And here we have physical dimensions of the module. So what's really easy in SketchUp is you can draw in any dimensions. So we know that this module is, just start drawing a line on the red axis or any axis. And we know that it's 1,960 millimeters long. start your line and type in 1960 mm because we want it to be in millimeters units. And we can zoom. And then it is 1000 millimeters wide. 0 millimeters. Just finish out that rectangle. Oh, have a rectangle. So the next order of business for this rectangle is to give it some depth. So if we look at the profile, it's 46 millimeters tall. We're going to go over to our model, use the pull tool. I do with hotkey P for push and pull. You just start your extrusion, then we type in 46 mm. Here we go. So that is a dimensionally accurate solar module. If we want to make it slightly more convincing, you can add in this outside rim. That is going to be another offset command, and that rim is 10 millimeters. Oop, I forgot mm, so you can just overwrite that 10 mm. We have that, and the underside 29 millimeters on the inside. It's good to have a front and back differentiation. So we'll click here, offset tool, that's 29 millimeters, and then we not going to worry too much about that dimensional accuracy, though we do know that it's probably about 30 millimeters. So there we go. Now, one other key point when you're modeling your solar panel, and may not be apparent now, but you may thank me later depending on how you work on your models. It's always good to denote the top up side, not the front and back, but what's top. If you're standing your model up here and looking at it, portrait, you want to know what is the top end. And over here, one easy way to do that is to just draw this junction box. So what I'm going to do is I'm going to flip my panel over and draw junction box. I'm not overly concerned with that being dimensionally accurate for this exercise. Frankly, it just doesn't matter as long as it denotes top, because it's near the top. And as you saw, I just snap that center to center, and then I can just move it up. And that does look a little bit out of place for that module if we're comparing it. But there we go. That looks pretty good. And now I'm going to flip this back over, bring it back, and there's our solar panel. Next important step is to make it a component. Make component, and we're going to call it an LG. We want to get the name right. Matters right here. Is an LG 365 N2W-B3, and that is a 365 72 cell. Don't need all those details, but can't hurt. So there we have it. That module is now created, and just realized I drew it kind of on the wrong axis. Typically in SketchUp, you want green to be your up-down axis. So what I'm going to do is I'm going to double click inside here. I'm going to move this entire thing so that this corner is on the origin. Then Q, I think I added that shortcut as well. Or rotate. Q kind of looks like a protractor. Now we've rotated it that its home point is on its own origin axis a little bit more accurately. That's another important tip that you will thank me for later. So now we have the module drawn and it lives. I'm breaking my own rules. It was on the offsets layer. We want it to be on the modules layer, but we want all of its geometry to actually be on untagged. It's a good SketchUp practice, and then your groups are tagged on the appropriate layers. So now the question becomes, where do we put this thing on the roof? Well, you have two options. There's really no denying that by far the most efficient layout of solar panels is facing due south, tilted up at approximately your latitude so that you get as much sun as possible throughout the course of the year. Unfortunately, that is not really practical for all buildings due to a number of different considerations. One being wind loading, two being structural loading. So the higher your modules are tilted up, the more they're going to act like sails. And if you have a bunch of sails on your roof, you're going to have to weigh them down with more ballast. And then when you add more ballast, then your roof structure has to support that. And on most retrofit buildings, there is definitely a limit with how much ballast a flat roof can accommodate. So what happens is the industry kind of standardizes to common pitches and common layout configurations, just like the Ford Model T revolutionized automobiles because of standardization and the precision tools that enabled that. So too has the solar industry. They've standardized. You can absolutely get custom parts and custom racking and one-off orders and made-to-order parts and pieces, but those are almost universally going to be magnitudes more expensive. So what typically happens is certain contractors, certain engineers, certain portfolio managers, they're going to standardize because they get pretty significant economies of scale. So for this exercise, what I want to do is look at just a couple options. We're going to look at two racking options, the EcoFoot 5D, and no affiliation with any of this equipment. It was just a data sheet that I was able to get off the internet rapidly. And this is a ballasted system. Let me bring it over here just so that you can see it real quick. This is kind of what a ballasted roof system would look like. Here we have landscape modules at a 5-degree tilt, and then you have these ballast blocks that hold everything down to the roof so that the wind doesn't blow it off the roof. The other racking option that I want to explore is from the same manufacturer, but it's called the 2 Plus. And if we look at that, it looks relatively similar, less ballast, and this is at a 10-degree tilt. So kind of an overview of our two options that we're going to work with for optimization. So if we get those out of here for now, the next consideration becomes, what is our orientation? So if we look at the satellite view, the satellite view came in, it's cut and clipped and cropped as from Google, effectively. I think it was Google. Yeah, Google Earth. Google Earth is very good at providing you north-south. And this building clearly is not north-south. In fact, it's almost perfectly 45 degrees away from north and south. So you've got multiple options here as far as, do you want your panels to be north and south, which would mean they'd be rotated kind of like that, or like that more than likely because we'd be doing a landscape orientation. or do we want them to be parallel and perpendicular to the building? The first iteration that I usually go through is parallel and perpendicular. I don't know why. It's kind of a 50-50 whether you can fit more panels in a parallel and perpendicular configuration that will offset the slightly decreased production numbers, or if it makes sense to fit maybe fewer modules on the roof but have them slightly more optimized for production by facing north or south. This project is in Pennsylvania, so you've got clouds in the morning, clouds in the afternoon, so you're really going to need to run the numbers, and we'll do that later. But for the purposes of my process, I typically go with a parallel and perpendicular orientation to start off with. So if we try and figure out which is got a more southerly component, and I would say it's kind of 50-50. We could get the protractor out and measure it. But I'm just going to draw it with our modules facing that way in a parallel and perpendicular. So we're going to rotate this module 90 degrees because it was drawn parallel and perpendicular to the facility. Make sure modules is active. And one thing I forgot in the layout is we need, get rid of the sat view. We need our perimeter. Let's see if I can bring that back up. Barcode. Go back to the split screen. Perimeter pathways right here. That nice big. There shall be a minimum 6 foot wide clear perimeter around the edges of the roof. That's pretty straightforward. Where either axis of the building is 250 feet or less, the clear perimeter around the edges of the roof shall be permitted to be reduced to a 4 foot minimum width. Where either axis, so that just means one or the other. Let's measure this thing. Easiest way to do that is to just draw a line. This edge to this edge, I don't know if you can see it in the very bottom right. That's 236 feet. 236 feet is less than 250. But if we were to include this, depending on your fire code, fire official, that's 258, and that is 267. So that exceeds it. So they may or may not be comfortable with that. However, this axis is only 114 feet. 114 is clearly less than 250. So we're going to say we're good with 4 foot offsets. So now we go in here, offset command, 4 feet. Same thing here. Just offset feet. And then this one, set 4 feet. Okay. So don't know. So I want just those lines to be on the offset layer. So what I'm going to do is I'm going to select these surfaces with double clicks and holding shift. That gets you the faces and the edges. So a neat trick is you just want the edges that are all associated with the face. You can then just single click to get rid of the faces while holding shift. The edges will stay. We will cut those, get out of the group. I actually want to go back into our offsets and obstructions group. Then we're going to do paste in place. So now we know that that has fallen into the offsets group as well. So later, when we're trying to show the model in a clean form, you can just hide your offsets and all these lines go away. So now we know we have a 4 foot clearance. So where do we begin our module layout? Well, the first thing is I want to explore this system with a 5-degree tilt. That is based on go foot 5D. We're gonna go foot 5D document and figure out what our spacing needs to be. So you can look into the specifications, see ballasted, attached, or hybrid. They give you the weight. They give you the tilt, 5 degrees in landscape. That's exactly what we know. And then the module inter-row spacing is 9.9 inches. There we go. We could have tried to calculate it based on the orientation of the sun, and as you get closer, you can have your modules butted up to each other, but as they start to pitch, they would shade, so you need to start spacing them out. That's inter-row shading. Go into that in more detail if people need, but for the sake of this exercise, we're just going to go with what the data sheet says, 9.9 inches. So we go into our module. Let's make this bigger. We go into our module. I'm going to hit Q again to get my rotate tool. I'm going to tilt it up 5 degrees. Just type 5. There we go. Now I want to, wondering why thicker. So if you hold the up, that'll lock you to the blue axis. Oh, that's why. That junction box is too deep. That's gonna push that. That's more junction box depth. Sorry, I'm mincing my words. Let's bring this back down to the surface of the roof and look at the data sheet. It doesn't give us a height, but if we take our best guess, that looks to be about 4 or 5 inches in the front elevation. That cinder block is probably roughly 4 inches, but it's an inch or two up. So it's approximately the same height from the ground. Like you could slide that cinder block under the module from the side. So I'm going to say 4 inches. Long story short, I'm going with 4 inches. You could call the manufacturer and get the exact info, but I'm just going to pick it up 4 inches. 4 inches. So now if we turn on shadows, you can see that it's elevating above the roof. Shadows for now, just to keep things speedy. The other consideration is how far away from the edge. So we could drag this over exactly over our offset, but that doesn't account for the extra space required. Once again, you would need that dimension, or you can measure it off of the cut sheet, but it's a pretty safe assumption that if you're 12 inches in, that's got you covered because the inner row spacing was 9.9. So if we go back to that consideration of inter row spacing being 9.9 inches, we know that we need to add a new module that is 9.9 inches away from this one. M for move command. I'm going to move tap control to toggle the copy function of the move command. We line these two modules up, and then I add 9.9 inches. That's the easiest way I've found. And then the other thing is, sorry, I'm checking my notes, is we want to add a little bit of space between the modules. So if you go in edge to edge, typically it's about 3/8 of an inch to an inch space between for the hardware. I'm going to go with 3/8. So I just type in 3/8 for 3/8. Now we have a 2x2 array. Now what I'm going to do is what I call bulk layout. So now that this is created, you can use the array command in SketchUp, which makes things really quite quick. Pick the two modules you want to repeat. M, Control to toggle copy. Just know that we want it to go that distance. So that slid this module up here. And then however many times you want that to repeat, you just type in and then X for 2X. But that's looking more like a 5X or a 6X operation. 7 is too much. That's not going to give us enough space on edge to edge. We're going to go 6X. There we go. We can center this up later if needed. So now we have that built out, and next item up for business is to lay this thing out the length of the again, and to move, Control, copy. See this sliding that back and forth right there. And what do you think? 35X? Way too many. 25X. We'll closing in on it. 24X. Let's look at the top view. 24 is just a bit too much, so it's going to be a 23X job. All right. Now, we want to try and center these modules around the building. So the easiest way to do that is to just hide everything beside the modules. We're going to highlight the modules, then we bring the building and the offsets back and grab the array. 1, 2, 3, 4, 5, 6, 7, 8 modules. So 4 to 4 is going to be the midpoint. You can just drag that to the midpoint of our offset right there. That's centered on the midline, but this is going to force us to not use that module. So we'll consider that later, but that module may be out anyway because of the shading from this. So we're going to leave it centered. We're going to take a quick look at our interference. But before we do that, and we really get carried away deleting things, we're going to once again center this north-south, approximately there. And then the next thing we want to do, because these three roofs are basically the same, maybe even identical, we're just going to copy the whole array. And we're going to copy the whole array again. And messes up this layout, so we know we want to once again shift these modules around. These modules look fine. These modules could stand to be shifted, so we're going to shift those point there. All right, so to avoid the offsets, can hit K in SketchUp. That brings up this hidden line option. Let's see if I can make this just a bit higher res or bigger for you, in case you're watching it on a phone. So you can see the dashed line show up of our equipment offsets. If we bring the obstructions in, becomes even more apparent. So obviously you can't have this module and this module because they're through a piece of equipment. Same here, those have to go. These modules need to go. So then I just go through and I start deleting modules that interfere. Those interfere. Those interfere. These look like they're interfering because of the offset issue, so those would have to go. Those need to go. This is telling me I probably want to shift the whole array 2 feet left. That may solve us a couple problems. So let's actually do that. Let's hide everything except for the modules. I want to move the interior surfaces of the building. Offset back. Just shift this. Yeah, that does actually give us right there. So we make up 2 right here, but we would lose 2 up here. Kind of 6 one, half a dozen of the other. we're modeling from satellite imagery, so these may not be super accurate anyway. So I'm just going to roll with it because we were able to get those back in. These two, though, would probably have to go. Now we move over here. Same deal. Wheaton. What you don't need. What you can't have. Pipes here. Clearance issues there. Probably gotta go. Need to go. Go in on it. Try not to take too long, but if you're working alongside me, or how you're making out in Revit, you're able to work this quick. There we go. Now we have our modules in here laid out. We haven't drawn the racking, but to communicate the idea and to do the initial testing, you don't really need the racking in there. In fact, it's just going to slow down your model anyway. So the next step after you've gotten rid of the obstructions is you need to consider shadows. And this is where I really, really like SketchUp. So I used to work with a colleague that, or he was my boss actually, phenomenal engineer. And he used to draw the shade cutouts by hand. He would calculate them with geometry and trigonometry based on the elevation of the obstruction, and then he would draw. They often looked like flowers because of the sun path, and he would draw those and he would stick them around on every piece of equipment, and then he'd cut his modules out. That was kind of what you had to do a couple years ago. You don't have to do that anymore, not since SketchUp incorporated sun path. I can't necessarily guarantee that the sun path in Google SketchUp is absolutely perfectly accurate. There's been white papers and research papers about it, so please research that yourself. I'm more than comfortable using the information that the algorithms in Google SketchUp have. What you do need to do, though, is geolocate your model. So you'd go into geolocation and add imagery. It says add more imagery for me because I've already geolocated this module. But you would go in, highlight, or find your address, highlight the building, and then you'd click select region. And then it would pin your model to its latitude and longitude. And then the sun path is accurate. So what I then do next is I want to cut out pieces of the array that are going to be in the shade. Kind of an industry standard is 2 hours around solar noon. So from 10 a.m. to 2 p.m. at the winter solstice. So we are going to turn on our shadow function. And we're going to turn it to winter solstice, call it December 21st. And then we'll go 10 a.m. So that's where the shadows are at 10 a.m. So that's an easy way to get a good clean view. You can right click on your axis tool and say align view. Beautiful. And nice and square to your axis. Could even change to parallel projection, and then that gets rid of parallax from your perspective view, which is kind of neat. So then I just go through, I have my sun set at 10 a.m. on the winter solstice, so that's the worst sun condition. You can clearly see that those modules are in the shade. Yeah, it's borderline. That's like a couple minutes out of the year. I'd probably let that one slide. However, from an equipment access standpoint, there's no clear, fast way. Apologies for the sirens. There's no clear, fast way for anybody to work on this equipment without traipsing through the array. So some modules need to go. You could probably delete these two, and then maybe this one, and then workers could walk through there. Same down here. You're going to need access to the array. for service, but those need to go. That one's got to go. That one's got to go. That's looking pretty good. These are looking pretty good. Pretty good. Pretty good. So then I just add a few hours. Let's look at noon. That's got to go. And it's actually sometimes easier to have the north view if you're not going to be highlighting your modules. Or have north up and down as opposed to building north if you're not going to be highlighting large groups of modules, because then your mind knows where the sun's going a little bit faster. So now let's add another 2 hours. Let's add another hour so we can see we've got some sun there and there. These are all looking pretty good. That's looking pretty good. Let's add another hour. That's looking pretty good. Nothing there. It's a tall piece of equipment. That's gonna go. That's borderline. Probably leave it. There you go. So that's looking pretty good. Put our camera back to perspective. Take a look kind of from the southwest here. And let's watch these sun paths. And 9. So 9 a.m. in the middle of the winter, yeah, you start to get some pretty heavy shading, but that's going to be pretty rare. And 2 in the afternoon, 3 o'clock, yeah, your shadows start to get real long, but that's also not going to happen because if you looked at this, in summer, June, July, August, it's absolutely a non-issue. 3 p.m., 4. Not really a big deal. So that is step 1. We've laid out the maximum theoretical capacity of modules on this array, and we haven't counted how many there are. We haven't considered how many modules are in a string, how many strings are in an inverter, but now we have approximately our physical theoretical maximum capacity at 5 degrees, parallel and perpendicular. There's optimizations that we're going to do later. We look at 10 degrees with additional row spacing. Can look at north-south, or even in this building, facing southwest instead of facing southeast. But for the purposes of this exercise, we're going to stop here because the 5-degree pitch is going to have, or tilt, excuse me, the 5-degree tilt is going to have the greatest density. And in the next set, we're going to start looking at the electrical characteristics. So in part 2, we will look at the number of modules per string based on the safe and optimal voltages with a open circuit voltage calculation, and then the number of strings per inverter for the maximum power point tracking capability of the inverter. Well, I hope you've enjoyed watching me click around on my computer screen, and see you next time. Thank you.